9.4 is graphing rational functions. A rational function is a function that's basically two functions split up into one. So in our previous lesson, 9.3, we did those reciprocal functions that were things like y equals 1 over x plus 2 or something. And that graph's called a hyperbola, but it's just 1 over x. We call it a reciprocal function. Well, rational functions are really if you take two functions, f of x and g of x, and divide them by each other. So for example, over here, here's our one function, we'll call this one f of x, and here's our other function, g of x. And because we have this division with x's on the bottom, we still have to worry about asymptotes. This box here shows the rules for the horizontal asymptotes. If the degree of the function on top, if the degree of f is greater than the degree of the function on the bottom, the degree of g, then there are no horizontal asymptotes. If the degree of f is less than the degree of g, like we have here, if the degree on top is less than the degree on the bottom, there's a horizontal asymptote at y equals 0. So this graph doesn't have an asymptote, a horizontal asymptote at y equals 0. If the degree of f is the same as the degree of g, if the degree of f equals the degree of g, the two powers are the same, there's a horizontal asymptote at the division of the leading coefficients. And I will actually show that on our first example we do, how that one works. So here's a graph, 6x to the third plus 5x squared over 2x to the third minus 2x. Right now the degree on top and the degree on the bottom are the same. So we're talking about this scenario here. Since the degree on top and bottom are the same, I know that the asymptote is at the division of the leading coefficients. So the horizontal asymptote is going to be at y equals 6 over 2, which is 3. I'm going to have a horizontal asymptote at y equals 3. Here. Now that I've figured out what my asymptote is, I want to see if I can simplify this at all. Well, the top can factor, I can pull out an x squared, and I have 6x plus 5. The bottom can factor, I can pull out 2x, and I have x squared minus 1. Well, one of these x's here cancels with one of these x's here. So as I simplify this, I actually get x times 6x plus 5 over 2x plus 1x minus 1. I got that x plus 1x minus 1 because this is a difference of squares that can still factor. So now I can tell that x cannot be negative 1 and x cannot be 1. Originally, in the original problem, we might have actually thought that x also can't be 0. So if x is 0 here, we get 0 minus 0, which is 0, and we can't divide by 0. But since the x on the bottom canceled when I simplified, it doesn't actually matter. That issue kind of got resolved when I canceled those x's. So I know that x cannot be 1 and x cannot be negative 1. I have these things here telling me that x cannot be 1 and negative 1. And those are two more asymptotes. I have a vertical asymptote at 1 and a vertical asymptote at negative 1. And my graph is going to be kind of framed by those three lines, which kind of makes 6 different sections. Now, something to know about asymptotes, the definition that we've been using isn't really complete. What I've been saying is that an asymptote is a line that your graph never touches. But a lot of times, you'll actually touch asymptotes around here somewhere. You'll get close to your asymptote out here. On the extremes, the more extreme you get, you don't actually touch the asymptote. But inside, around there, you can touch the horizontal asymptotes in this area here. This area here, you can touch horizontal asymptotes. You never touch vertical asymptotes. And I think we'll see that here, but we'll see. Okay, here's how you graph this. I'm going to take my two asymptotes, x equals negative 1 and x equals positive 1. This is really what x can't be. X can't be negative 1 and x can't be positive 1. So I'm going to make tables that are around those points. This table will plug in numbers that is less than negative 1. This table will plug in numbers that are greater than positive 1. And since negative 1 and 1 are so close to each other, at this table I'll plug in numbers that are between negative 1 and 1. I'm not smooshing them together. I'm going to plug in numbers between negative 1 and 1 for that middle table. And this can all be done on my calculator, thank goodness. Let me go to my y equals menu. I have to type in the simplified version that I have. I'm going to type in this version here with the x squared, so 6x plus 5. So it's going to need a lot of parentheses. The entire top has to be in parentheses. Oh, I guess I'm going to type in this one here. So on top, I'm going to do x times 6x plus 5, double parenthesis, divided by, double parenthesis, well, I guess just one parenthesis to start, 2 x plus 1, x minus 1. Yep, that looks good. Now I'll go to my table. I want my table to be set up to ask, so I'll go to my table set and have it set on this ask one right here. I'm going to plug in numbers that are less than -1. The numbers that are less than -1 are like -1.1, -1.5, -2, -3, -4. So -1.1, -1.5, -2, -3, -4. Those look good. I have 4.2, 2.4, 2.3, 2.4, 2.5. So they kind of go down and back up again. Now remember, this horizontal asymptote was at 3, and here we're crossing over 3. This graph is actually going to cross the asymptote. -1.1, 4.2 is up here. Just say it's there. -1.5, 2.4 is here. -2, 2.3 is here. -3, 2.4 is back up here. -4, 2.5 is here. So this graph's going to go like this. And it's sort of this weird curve. And I'll actually graph it in a second with the computer and you'll see. And I'll do the middle pieces. I'm going to plug in numbers between -1 and 1. So it's like -0.9, sure, and -0.5, and 0, and 0.5, and 0.9. Those are all numbers really between -1 and 1. But I'm going to try to make some more space for myself when I do this. -0.9, -0.94. -0.5, 0.67. 0, 0. Really? Yep, I guess so. And 0.5, -2.3. 0.9, -24. It's very low very quickly. I'll try and graph that as best I can. -0.9, -0.9 is basically here. -0.5, 0.67 is kind of around here-ish. 0, 0 is here. 0.5, -2.3 is here. 0.9, -29 is way down here. So this graph is following this asymptote and then it goes, has its little spike, and then comes back down. That asymptote. Plug into the third piece, I plug in 1.1, 1.5, 2, 3, 4, but I think you kind of get the idea of what happens. I just plug those in and see. So what I can do now is just show how this actually graphs. If I drag this little box over here, it graphs like that. You can see my blue lines are pretty close to the actual purple lines. Not perfect, but pretty close. So that third piece, had I actually plugged in these numbers, would have followed this curve over here. And that's your rational graph. Graphing it by hand doesn't look super pretty, but you plug in points into your table and just kind of go for it. It's not so bad. We'll do 2 more examples. Here, the degree on top and the degree on the bottom are again the same, just like they were over here. When the degree on top and bottom are the same, I find the horizontal asymptote by doing the division of the fractions, or of the coefficients. That's 1/2. This will be the line y equals 1/2, which is right, yeah, here. I've already graphed it. You can see the points that are there. To find the vertical asymptote, I factor. Well, I'm going to factor everything and see what happens. So the top factors into x minus 4, x plus 3. bottom into, I know I need a 2x and x. If I do 4 and 1, yes, minus 4 plus 1, that's how that factors. These cancel, so I'm left with x plus 3 over 2x plus 4. So my vertical asymptote is at negative 1/2. X cannot be negative 1/2. That's my vertical asymptote, which you can see here. Now, to make this graph, by hand, you would plug in points into your calculator. You would plug in points that are less than negative 1/2 and points that are greater than negative 1/2. So that's points like negative 0.6, negative 1, I guess, negative 1, negative 2, negative 3, and then negative 0.4, 0, 1, 2. So plug in points like that, but you would get out this. This is another example of a hyperbola. Whenever you have just these two curves that are symmetric, that's what's called a hyperbola. Not hyperbola, but hyperbola. One more, the degree on top is bigger than the degree on the bottom. Since the degree on top is bigger than the degree on the bottom, this has no horizontal asymptote. And again, as you can see, I've graphed it. There's no horizontal asymptote that the graph gets closer and closer to. You might be thinking, wait, isn't there some weird diagonal asymptote like this? There totally is. We're not going to worry about the diagonal asymptote in this class. It's actually called an oblique asymptote. It can only happen if the power on top is bigger than the power on the bottom. There can only ever be one oblique asymptote. But that's a pre-calc topic, not a not a IITrig topic. What I'm going to do, though, is just factor the crap out of this thing. The top is a quadnomial. It has 4 terms. So I'm going to see if it can group. If it can't group, sweet. If it can, I'm going to group it. I can pull an x squared out of that first half, and I'm left with x plus 4. I can pull a 2 out of the second half, and I'm left with x plus 4. So I get x squared plus 2 times x plus 4. That's what I get on top. On the bottom, that just becomes x plus 4, x plus 1. Well, the x plus 4's cancel, so this is really the graph of x squared plus 2 over x plus 1. So it has a vertical asymptote at x equals negative 1. And that's what this is right here. There's the line x equals negative 1. I haven't been doing my domain and range very well today, so domain is all real numbers except negative 1. In this case, the range is going to be kind of tough to find. I'm actually going to estimate it, because the range is all the numbers, it's all numbers y such that, well, here, the lowest y value we'll say is 1.5. So y is greater than 1.5, but it's also less than negative 5.5. And that's just an estimation. Maybe later I'll show you how to actually calculate that precisely. But that's just an estimation of my domain and my range. There's my graph, which I again can find by making tables and plugging in points. I think that takes care of this. Thank you very much.